Perspective Class 8 Video 2. In this video we're going to talk about some properties of parallel projection. So let's go on to the first theorem I want to talk about. This theorem simply says that parallel projection maps parallel lines to parallel lines, or points. Okay? Because there's always a chance that when you parallel project a line, it might collapse down to a point entirely. This is the case where the line is perpendicular to the viewing plane. But in general, parallel projection maps parallel lines to parallel lines. And this is quite a useful theorem, because you can use this theorem to tell if an image has not been created with parallel projection. So you can use this to tell that certain images have been created with some other type of projection. So for example, if we look at this image right here, this is two images of the same scene. So it's like the interior of a house, there's like a couch, a window, a table or something, I don't know. So two different images of the same three-dimensional scene. But we see that the left scene, these lines are not parallel. Like, they seem to like converge a little bit. They're not parallel. The red lines are not parallel. But you know, in real life, this room, the floor tiles, the lines are parallel, right? In the real world object, the real world scene, the floor tiles are parallel. So it means that in the creation of this left image, the parallel lines have become not parallel. So that means that the left image was not created with parallel projection. So, not using parallel projection. Okay. In the right image, the lines are parallel. Okay. Do you notice like all of these floor tile lines, they remain parallel in the right image, and not just the floor tile, but all of these lines, like they all remain parallel in this image. So it's likely that the right image was created with parallel projection. So probably using parallel projection. It is worth noting that the left image is probably more like photorealistic. It seems more natural than the right image. The right image, all these blue lines, they're parallel, but this feels wrong. This isn't what the scenery would look like if you were actually in the room. You wouldn't see this with your own eyes. What you would see would be more like the left image with the red non-parallel lines. But we'll get onto that at a later date. Let's move on to another property, or another couple properties. So, theorem. Parallel projection preserves or shrinks the length of lines. Okay? It typically shrinks them. So parallel projection typically shrinks lines, shrinks the lengths. And the second part of this theorem simply says parallel projection typically distorts angles. Okay? So what I mean by this is, you know, three-dimensional objects, they can have angles, but after you parallel project them, those angles might not be the same. Okay? So let's look at an example. In this example, I've just parallel projected a cube from three different angles. So you should imagine a cube in three-dimensional space, and I've just taken three different parallel projections of it from slightly different angles. Okay, so it's the same cube, same size cube every time, just a slightly different parallel projection from a different angle. And what are some things to notice? Well, one thing to notice is the edges remain parallel. Like this edge and this edge, they're parallel. Whatever, that one and that one, they're parallel. And this is true for all of the cubes. Like, parallel edges remain parallel. So even though like the cubes look different, they each preserve this parallelness of the edges. Okay, so notice that the parallelness of the edges are the same. Angles are distorted though. So for example, if you consider this angle right here, well, you know that if this was actually a cube, that angle should be, I should be able to spell, it should be 90 degrees, okay? But this is more than 90 degrees. This is more than a right angle. Similarly, this angle should be 90 degrees, but that's less than 90 degrees now. And for a really extreme example, this angle right here should be 90 degrees, but that's obviously much less than 90 degrees. That angle right there, that's much less than 90 degrees. So the angles get distorted. These properties, they might be a bit surprising and a bit like counterintuitive, because you're probably so used to seeing pictures like this that your mind automatically sort of fills in the gaps, and your mind tells you that this angle here is 90 degrees. Even though it looks nothing like 90 degrees, your mind sort of tells you it is 90 degrees. But if we objectively look at this picture, that is not 90 degrees right there, and it should be 90 degrees. The other thing I want to notice is the lengths shrink, okay? And again, you can see this most prominently in the third picture. So this is a cube, so all of the edges should have the same length. But obviously, this length right here seems a lot shorter than that length right there. It's not in real life. In real life, they're exactly the same. But in this particular parallel projection, it looks like this length here is shorter than that length there. So this example shows that parallel projection does not preserve angle. In general, parallel projection distorts angle, and in general, parallel projection shrinks lengths. Okay, but I mean, that's not the end of the world. You are asking for a method of taking a three-dimensional object and making it two-dimensional, and in doing so, you're going to lose some information. It's natural that when you take a three-dimensional object and you squish it down to 2 dimensions, you're not going to be able to preserve everything. Okay, so in parallel projection, you can't preserve angles and you can't preserve lengths. But parallel projection does preserve parallelness of edges. So if edges are parallel in 3 dimensions, they remain parallel after you've projected them. Okay, so this is the end of this example, and this is the end of this video.